Okay, picking up on video part 3 of 4.2 on area. And here there's a theorem, 4.3, limits of lower and upper sums that let f be continuous and non-negative on the interval. If it's continuous and non-negative on the interval AB, the limits as n approaches infinity, both the lower and the upper sums exist, as long as they exist, and are equal to each other. The limits as n approaches infinity of both the lower and upper sums exist and are equal to each other. And that's just what we were talking about when we had the limits as n goes to infinity. We pictured, oh, it's got to be 8/3. Okay, because if you notice, the 8/3 is the only thing that's left as n goes to infinity. Those two terms drop out and become 0. So where delta x is equal to b minus a over n and f of m sub I and f of capital M sub I are minimum and maximum values of f on the subinterval. So we're going to do one of these problems with limits then, and we have the function x cubed here. So find the area of the region bounded by the graph of f of x is equal to x cubed. And we want to get the exact area, okay? The exact area where it's bounded by the function x cubed, the x-axis, boom, and the vertical lines x is equal to 0 and x is equal to 1. So you see the area is shaded there. So I have the limit set out, and I need then my x sub I, and though my x sub I is equal to where you start, and we're starting at 0 again. We don't always start at 0, but I'm going to do I. Since they are equal, I'm going to do a right-hand. Okay, and my delta x is pretty easy. It's 1 over n then, right? So that's pretty easy to just stick right in there, and then we can talk about delta x being that. So it's going to be I over n, because delta x is 1 over n, right? Okay, so there we go. And delta x, I'll write that here just to have it listed. So it's going to be 1 minus 0 over n, or 1 over n. Okay, so now we have my two components here. So now I'm going to get the area is equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of f of, so this is going to be, here's my x sub I going in. My x sub I is I over n, and that's going to be cubed. So there's the function, and then times 1 over n, the delta x. Okay, so now I'm going to go ahead and cube that, and so I get the area is equal to, I'm going to switch over to black ink. So we have the limit as n approaches infinity of the summation from I is equal to 1 to n of I cubed over n cubed, and then this is times 1 over n, and I'm going to simplify it one more time. So this is as n approaches infinity, we have the summation from I is equal to 1 to n. I end up with an I cubed. And what I'm going to do is I'm going to pass the 1 over the n to the 4th out in front of the expression here. And I'm going to put it right in front of the summation. I kind of have my choice as far as what I can do here. I can put it in front of the limit, or I can put it in front of the summation. So there it is. Okay, so now that I have I cubed, now you got to remember what the summation of I cubed is going to be n times n plus 1 and over 2, and then it's going to be squared. Okay, so with that one then, we now have the limit as n approaches infinity of 1 over n to the 4th. And then so we have, I'm going to plug in, but I'm going to plug it in like this. I'm going to go ahead and square that, so I get n squared times n plus 1 squared over 2 squared, which is 4. Okay, now there's some algebra that I'm going to skip around here a little bit. I'm going to then take this n squared and make this a 2. Okay, and we have a 4 down below. So then we have this. This is equal to then the limit as n approaches infinity. Then I end up with an n squared plus 2n plus 1. And that would be over 4n squared. Okay, now you can see already, so this is going to equal, without doing any other kind of manipulations, you guys are looking at the leading terms here. So you're going to look at 1n squared over 4n squared. With a manipulation of dividing all the terms by n squared, you could do that if you had to prove it. But sometimes you just want to go ahead and get the answer here. So this is going to be 1/4, right? So the area equals 1/4. the area that we're talking about under the curve, the area under x cubed, okay? So everybody all right with that? Just check that out if you want to look over the steps and see if you have any questions about that. Okay, and let's go on to the next one. So we're going to do the same thing here, but we have 4 minus x squared here. So with this one, 4 minus x squared is our function. We're going to start out what x sub I is. We're going to pause your video and try the x sub I and the delta x, and then come right back to it. So with this one, we have area is equal to the limit as n approaches infinity. I'm just going to write this stuff in here. So I is equal to 1 to n. Okay, so we're going to start down here, and I could use a c if I wanted to. I know that your textbook uses a c for the x sub I, c sub I, as a different constant, that point in question. I'll use that sometimes. But so let's start with x sub I here. Where we're going to start our interval is 1, okay? And I wanted to do 1 like this where I wasn't starting at 0. So it's going to be 1 plus I times delta x, right? And we have our delta x here. We're going from 1 to 2, right? So I'm going to skip a couple steps. Delta x is then equal to 2 minus 1 over n, or it's just going to be 1 over n, okay? So your x sub I is then going to be 1 plus I times 1 over n. Oops, didn't mean to do that. I times 1 over n, or that's equal to 1 plus I over n. Okay, it's always where do you start the interval. If you need some review on that, I can give you some helpful hints. Okay, so we have now f of, I'm going to write this up here without scrolling too far. It's going to be 1 plus I over n, f of that, and then it's going to be times the delta x, which is 1 over n. Okay, so now remember your function is 4 minus, so what you're really looking to put in there is 4 minus x sub I, right? So we have our x sub I already substituted in here in the functional notation. So we now have area is equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of, then I'm using the function, I'm going to use a bracket here. So it's going to be 4 minus, and then it's going to be the quantity. Here's my I going in. So 1 plus I, I'm sorry, my x sub I going in over n, and it's going to be squared. So there's my function, f of. So let me highlight this really quickly. So let's use some green here. So this notation is the whole enchilada. Okay. So, and then I'm going to multiply by 1 over n. Okay. All right, now we just have a little simplification to do here. So we get the area is equal to the limit as n goes to infinity of the summation. So we're going to do a little algebra. So with that, then we now have the summation. Let me see, we get 4 minus, we have to square that, right? So we could square that off to the side. I think that we should get 3. I'm going to let you handle this off to the side on your own. But remember, we're going to have a 4 minus a 1. So we're going to have a 3, and then it's going to be a minus. You have to distribute the minus sign. So you should have a 2i over n minus I squared. So over n squared. I squared over n squared. And then we have that times 1 over n. Okay, so then next we're going to distribute that. So we have area is equal to, we're going to distribute the 1 over n. So the limit as n goes to infinity of the summation from I is equal to 1 to n. And so I end up with the summation of 3 over n. And I'm just going to go ahead and distribute the n then to that 2i over n squared. As you'll see, it's kind of convenient at times. I squared over n cubed. And then there's shortcuts that you'll see right away after you do hundreds of these problems, maybe thousands. I'm just kidding. Okay, so with this one, then I'm going to say, I'm going to take the limit as n goes to infinity, and I'm going to write all these out. So the first one is 3 over n, right? That's just a number. That is just a number. So yeah, I'm going to go ahead and make a bracket and separate these so it can be clear. I is equal to 1 to n, and then it's going to be 3 over n. That's just a number. And then minus, then I'm going to do the summation from I is equal to 1 to n. So what I'm doing is the summation of a sum or difference is equal to the sum or difference of the summations. So then I have this is 2 over n squared, and this times I. And I could pass that, actually, why don't we pass that out front? That's a constant. It's convenient to do that, right? And we'll just put this in here, but I don't like that little dot there. I'll take that out of there. So this is just the summation of I. I'm going to move this here. I'll put that 2 over n squared in front. Okay, like that. Okay, and then I have this. And then I'm going to pull this 1 over n cubed out front, and then times the summation of I squared. So I have all my I expressions and my limits of a constant, or the summation of a constant, in the right places. So with this constant I and I squared, I get to work substituting in my expressions. So I have A is equal to then the limit as n goes to infinity of, I have 3 over n, I'm going to times n. Okay, that's just a number, right? That's just going to be 3. Minus 2 over n squared, and then that's going to be times the summation of I, which can be replaced with an n times n plus 1 over 2. And then I have minus 1 over n cubed, and that's going to be times the summation of I squared, which is then going to be n times n plus 1 times 2n plus 1 over 6, okay, and bada bada bing. Okay, so what you're going to do is you're going to get very familiar with these and the way they look, and you're going to get familiar with the leading terms of what these expressions would turn out to be, because that's what's going to be key here. But I'm going to divide it out the first time, or I'm going to multiply it out. So we have n goes to infinity. We're just going to have a 3 minus, and if you remember here, now we're going to distribute here. We're going to take the 2, not distribute to the n. I should write it like this. So I'm going to distribute here and then multiply it by n. So I'm going to get 2n squared, 2n squared plus 2n, and that's going to be over 2n squared, right? And then I'm going to have minus, I'm going to have 2n cubed over here. So we're going to 2n squared plus 3n squared, right? Because you're multiplying the quadratic, you're multiplying that 2n squared by another n. It's going to make it 2n cubed plus 3n when you multiply doing the FOIL. And then we're going to multiply by n, give us the 3n squared. And then after a while, you just be like, oh, I got this. So it's going to be n here for the constant, right? But then in the denominator, we have a 6n cubed. So after a while, you'll really get in tune with these, and you'll go, oh, okay, well, this is the guy I need to be worried about here. After a while, you'll just rely on that, realizing that, oh, the limit's going to be 1/3 there, right? So then I have the area is equal to, let's go ahead and take the limit. The limit of a constant, the first term, 3. It stays the same, 3. Minus the limit of the next term is going to be just 1, 2 over 2, 1. And then the limit of the last one is going to be 1/3. It's going to be minus 1/3. Okay, so what do we get for an answer here? So we have, if I talk about this in terms of thirds, what do we have? If I make this 9/3, minus 3/3, and then minus 1/3. So it looks like I get 9 minus 3 is 6, minus 1 is 5/3 for an answer. So it looks like the area, let's just put it here because this video is getting long. This is just one problem. It's so much fun. Okay, so we get an area that is 5/3, okay? And this is example 6, okay? So I'm going to stop the video at this point. I'm going to pick up with another video for example 7, okay? And I'll see you when I see you.